traceability, then tell you a little bit about what's been going on in the tracing world with respect to the researchers, tell you a little bit about something called TraceLab, and then transition into a discussion about the TraceLab player, which is focused for practitioners, and then we'll have a demo and follow up with some questions. Back in 2005, we kicked around an idea for forming a Center of Excellence for Software and System Traceability, and this actually was inspired by some different NASA Centers of Excellence. A number of us attended the first COEST meeting under the St. Louis Arch at the International Conference on Software Engineering back in 2005. And I attended that meeting, as well as Jonathan Miletic from Kent State University, Giulio Antonio, he's at École Polytechnique de Montreal, Alex Dektiar, some of you might remember him, he's now at Cal Poly, Jane Cleland Huang, who's at DePaul University, myself, and a number of students. And I just noticed that this picture was actually taken at the IV&V facility in 2006, and I was noticing that there, my clothing is gray and my hair is black. Okay, so anyhow, so we actually had a lot of early success with the Center of Excellence, and NASA funded this Center of Excellence to start. So this, to me, is quite a feather in the cap for the NASA IV&V facility. By 2006, we had a mission, a vision, elected officers, we had members, we had this website that you're looking at here, and we had a two-day workshop here at the IV&V facility in 2007 where we started to look at the grand challenges of traceability. And we were thinking a little bit about what exactly it meant to try to help the practitioners. Give me just a second here because I have to find my way. Oh, no. Okay. I'm finding my way here to the website for the Center of Excellence for Software Traceability. When we put together this website, we were thinking that our audience would be mainly researchers, but we were hoping that in the future we would have some content for practitioners. So if we take a look at the website here, and it's coest.org, you can see that under About, we have our mission, our vision, members, officers, and how to join. And it's free, by the way. We do ask you for your email address and a bit of information, but there's no cost. Over here under traceability, you can see that we've been working on a body of knowledge, and one of the things that I find very helpful is a glossary that we have there of standard terminology in traceability to try to get everyone to use the same terms. Then we have this link for TraceLab, and I'll be talking about this at length, but I wanted to point out here, if I've inspired you enough by the end of this talk, which I hope I have, and you decide that you want to go get TraceLab and the TraceLab player, this is where you would come on the website and you would click on TraceLab download. And then over here under research, we have a number of different research projects and resources, including these grand challenges of traceability, where we had this two-day workshop and we tried to identify what we thought were the things we really should be working on in order to assist the practitioners. And of course, we're always interested in whether or not we've gotten that right, so please feel free to take a look at that. And then on the far right, which I think I'm not going to be able to show on the screen, there are some other resources which include tools, data sets, and other things that you might want to obtain. And again, all of this is free of charge if you don't mind giving us your email address and just a little bit of information. Okay, so I think anyone that's doing IV&V knows that a traceability matrix or a trace matrix or a requirements traceability matrix, however you refer to it, is a very important item and is used as the foundation of many different important IV&V activities. And I have just a short list here, but certainly, I think everyone would agree that you can't undertake criticality analysis, risk analysis, and some of these other techniques if you don't have a trace matrix. But the problem that we run into is that either the trace matrices are being generated manually, where folks are having to maybe even in an automated tool, they're having to pick from a drop-down menu the different links or do keyword searches, or if they have some type of a tool, they're finding that it's cumbersome to deal with, or if things change, then it's cumbersome to go in and try to update the links. As researchers, we've then been looking at a number of different ways to address this problem of creating and maintaining trace matrices. This can then be a little bit of a problem because practitioners maybe are a little overwhelmed with all of these different techniques and tools that are out there. And it might be difficult to understand how they work or what would be the best one to select. I give a list here of some of the different tracing techniques that are currently fairly popular. The most popular one is listed here at the top, the vector space model. And this is basically an information retrieval technique that's used in a number of the search engines. And you might have also heard it referred to as term frequency inverse document frequency weighting, or TF-IDF. So this is definitely one of the most popular tracing techniques, and it's also very, very powerful. You might have heard of some of these others too, latent semantic indexing, or LDA, or probabilistic. What we have found in general through our research is that these techniques are fairly good at finding the links that they should, but they also unfortunately return a number of false positives. So we have a problem with low precision. We have what's called high recall, but low precision. So we've been working on improving the precision, and we've tried a number of different techniques in the international research community, including using a thesaurus so that we can capture synonyms and acronyms. Also trying ideas of capturing some semantic information using phrasing. So instead of just using an individual keyword from each element to do matching, we try to use phrases. And of course, since we're research organizations and we're interested in getting publications, because almost all of us are academics, and of course we all know what the rule is with academics, right? Publish or perish. You see that a number of the different research groups have developed their own tracing tools. And there's sort of a plethora of these tools out there, and it might be difficult for you to know which tool to get. Maybe you're not even particularly interested in the front end of these tools and having to deal with the graphical user interface. This happens to be one of our tools, which is requirements tracing-on-target.net or retro.net. And we have, by the way, done quite a bit of work on this lately for MTSI and John Haynes and his crew in Huntsville. So if anyone is interested in a tool that has a front end, please let me know, because we'd be happy to send this to you. And there, again, we've had funding from NASA and National Science Foundation to develop this, so it's gratis. It's your taxpayer dollars at work. So, but with this, it can be a little bit difficult for folks to know exactly what to do or which techniques to use. So, or if you're a new researcher starting up, there can be quite a learning curve and quite an amount of work that goes into getting up and going. So we had this idea of coming up with TraceLab and building a tool similar to MATLAB, where you could basically take advantage of work that had already been done and very easily compose these tracing techniques, or we also refer to these sometimes as experiments. This would make it easier also for us researchers to compare our techniques to each other. So if Jane Huang had a technique at DePaul University and I had another technique, we could run both of our techniques on the same data set and compare the recall and precision. And this is actually how the phrase experiment or contest came up, because the idea was I can put my tracing technique in there and I can design an experiment to see how well it does against a certain data set. Jane can then basically pull out my technique component and put in hers and run the same experiment and see how well she does. And the idea is that we would have a leaderboard that would let practitioners know sort of which is the technique that currently has the highest recall and precision for any given data set or benchmark. So here's just a quick overview of TraceLab. You can see that It's a visual environment. It basically lets you design and execute these experiments or techniques. We have a component library, and you can pick from the different components that are available. You can basically write components in a number of different languages, including C# and Java. It has a very flexible workflow engine, and it works for a number of different operating systems. So you can use it on iOS, you can use it Linux, Windows, and it has a pretty intuitive user interface. Basically, once an experiment has been set up, you just have to go in and let it know where it should expect to find the input files and where it should expect to send the output files. And you can also configure some other parameters, including telling it the file paths. And as I said, this is really encouraging reusability. Besides being able to build individual components, you can also package the components. So for example, DePaul University has some packages of all their components that deal with a particular portion of tracing, and we have our own. When we were thinking about this, we thought, well, you sort of have to design these experiments at TraceLab, and you've got this canvas, and you're dragging and dropping in things, and maybe practitioners really don't want to mess around with that. One of the things that I heard from John Hayes is he wanted to be able to easily put our techniques on all of these different machines, and they had to go through all these different hoops to get permission to install things on the machines. And we thought, well, what if you could just have something that is basically a TraceLab player, where you could say, hey, I really like this technique or experiment, and I just want to be able to execute it over here on this machine. I don't want to mess with TraceLab or the canvas or anything like that. So that's how we came up with this idea of the player. Besides letting practitioners use it without having to interact with TraceLab, for researchers, it's nice because it can let us run multiple experiments at the same time. And basically, you have all the information that you need about the experiment or the technique, and then away you go. So before I go into the demo here, I'm going to show you TraceLab. And basically when it comes up, you'll see that the main section is a canvas on the right, and you'll see that it's got a precedence graph. So this, we refer to this as a technique or an experiment. And what you can see here is this is just a standard tracing technique. In this case, we're using that vector space model method that I mentioned earlier. And what you can see is that it's a precedence graph, and basically the outputs from one of these components is the input to the next. Okay, very straightforward. So here you can see this particular component is going to import your source artifact. Let's say you're tracing from requirements to design elements. So your source artifact are your requirements, and your target artifact are your design elements. In this case, we can import in a number of different formats, XML, comma separated value, or plain text. In this case, we're using an importer that's looking for a directory of files for the source artifact. And in fact, we have, I can show you here what that looks like. It's in the TraceLab player directory, and you'll see it's just a folder right here, input source. And each of these elements that are inside the input source are just individual files. Perhaps, I don't know what just happened there. Okay, well, here's an example of one of the requirements. Okay, just a typical text requirement. These are just text files. Okay, so back here on the TraceLab canvas, we can see that we also import the target documents, and then it goes through and does some pre-processing, and then it applies this vector space technique, and what it outputs is the trace matrix. Now, for each of these, if you click on the eye, it brings up a box, and if you click on configuration, you can tell it where you want that file to be, what the path is, what name you want it to have, and so on. So what we've done for a number of these different experiments or techniques that we think practitioners would like to use is we've basically hard-coded the name of the folder, the name of the files. Okay, in this case, it's in TraceLab player, and it's expecting a folder called input target. Okay, so now that we know about that, let's take a look at the TraceLab console. And all you have to do to run the TraceLab console is when you do your installation, it's going to put it in this path here, COAST, TraceLab bin, TraceLab console. And we basically just have to open that file. You see it up back here on TraceLab, which is behind this window. You can see the name of this experiment file, okay, demo.teml. So all we have to do is open that. Now this will take just a second, and then it's going to tell us some information about the technique or the experiment. So there you go. And then we just type run. And it's going to actually run this experiment. So it'll tell you the status as it's going through. It'll say, okay, I'm accessing the experiment. That's going to tell you that it's starting to process the experiment. And if I recall correctly, the first thing it does is it brings in the source artifact, and then it throws away what we call stop words, things like the and of and in that really don't help with tracing. But those types of words just give us even more false positives. Then it's going to go through and actually do the similarity comparison between the source and the target artifacts. And then it's going to output this file that has the trace matrix. And this should hopefully just take a second here. While I'm waiting on that, I did want to mention to you guys that a number of my colleagues and I, including Robin Lutz, maybe a number of you know her from JPL and Iowa State, we're working on a proposal to the National Science Foundation to improve tracing techniques for safety critical product lines. So we're looking for folks who might be interested in that type of work, and it doesn't cost anything. If anybody's possibly interested in that, feel free to let me know. We're kind of putting together our proposal on some different projects that might be interested in the work that we're doing. Okay, now it tells us that the experiment is done. So if we go here, okay, we go here, and we go back here, and we look at the file that was most recently modified. It should be at the top here. There it is, our output similarity matrix. And what we're going to see when this comes up on the left-hand side, we're going to see the identifiers for all of the source elements. And then the next column are the target elements, and then a relevance or similarity weight. And you can, of course, sort this file by the source identifier. Right now, the file is sorted by the similarity weight. It's also possible to use a batch file to do this. So it's also possible to use a batch file to do this. This is taking a second to come up here. Okay, there we go. So you can see the links. So this is requirement 13 pointing to requirement 88, and these are the difference relevance weights. Okay. Okay. So, all right. Now, you can also do a batch file, but I won't worry about showing you the batch file. But you can imagine that you can put those two commands with the open and the run and so on in a batch file and just have your folks use a batch file. Okay, so the next thing that I want to do is, before I take some questions on the TraceLab player, is I want to have one of my PhD students, Mark Hayes, come up and talk for just a few minutes about his research. He's doing some research in the area of testing, and I know that as IV&Vers, you all do quite a bit of independent testing. So I'm going to go ahead and turn it over to Mark, and he's going to talk for about 3 minutes.
Thank you. Yeah, so my name is Mark Hayes, everyone. I'm a PhD student with Dr. Hayes here at the University of Kentucky. More to the point, though, I have a background in industry at IBM. I work on an open source project called the Dojo Toolkit, which is an AJAX framework to make sure that browsers behave the same. So I test Dojo. I'm a software tester at IBM. And just like most software testers, we have a process. We try to make sure that our code is covered. But what we find is that even though our code is covered, sometimes that covered code still has bugs. Our test cases get defined. Our customers say, hey, did you test this code? We say, well, of course we did. So what went wrong? So we'd like some way of instilling confidence that we've tested but not only that we covered our code, but that we tested well enough. And so to examine this problem, we look at this notion of software testability. Maybe you've heard of the McCabe cycle-mat complexity. That's an example of software testability. We try to get an idea of whether a code is easy to test or hard to test. But there's a problem just using a McCabe cycle-mat complexity as is. The problem is that if you have this huge function, cycle-mat complexity just assigns one complexity value to this entire function. Maybe it's like 100 or something. So you know that this function is hard to test. But the problem is that you don't know what exactly about this function is hard to test. So in my research, I examined a different approach. We look at per line measure of testability. So for each line in that function, we assign a testability value. You might ask, how do you do that? Well, it's in the same vein of cycle-mat complexity. Basically, a simple way of doing it would be, say you have an existing set of test cases. What you could do is actually count how many times each line of code in that function you're testing is being executed. Lines are executed at least, say, one time, are the hardest lines to test, because your test cases are only covering them once, so you're not covering other angles. But now what? So in that case, you might imagine. So if we want to instill more confidence in our testing, we just test those lines which are being tested least, right? Add more test cases for those lines. Let's say you're very early on, you don't have test cases yet. Then what do you do? You can measure this testability, can you? So let's go back to McCabe cycle-mat complexity. It actually counts how many paths are through the function, basically, how many execution paths are through the function. So what you could do is actually figure out what these paths are. Then you can figure out how many times a line is covered by those paths. And so intuitively, the lines that are hardest to test would be those lines which are least covered by these paths from cycle-mat complexity. And so that's our approach. So does it work? So I looked at some bugs in Apache HTTP server. It has a SVN log of many known bugs. So I feed these bugs back into Apache. And I looked at the cycle-mat complexity of the functions containing those bugs and the testability according to my measure of those lines that were changed. And I found that using my measure that we were able to find more bugs compared to the McCabe cycle-mat complexity. We were able to predict where they would be. So that's the recall. We were able to find more bugs. In terms of the precision, both methods did terribly, right? McCabe cycle-mat complexity uses no information for your test set trying to find the bugs. So and so it had terrible precision. And the same was my case. I think it was like, both of them had like 0.2 precision in Apache. It's just atrocious. So what can we do with this information? Clearly, we can decide where we need to write more test cases. But more to the point, we can figure out how to refactor our code to make it easier to test. If you have a function that has many test paths, you can actually probably eliminate a lot of those test paths just by pulling the most complicated code out into a new function. And by using this testability measure, we can optimally refactor your code to maximally remove the number of test paths. So in terms of our future work, obviously we'd like to improve precision. In terms of, I'm a PhD student, of course, in terms of my dissertation, what I'd like to do is use this work in testability to answer the question, what is a fault? Why do test cases fail? And why is it that some faults cause more test cases to fail than others? So with that, I'll turn it over to my colleague, Ben, who's doing some formal verification.
Hello, everyone. So my name is Huang and I'm one of the PhD students of the case. So here I will introduce to you my research, that is consistency checking of natural language temporal requirements. So as the name implies, our work focuses on natural language requirements because these requirements are common. And we focus on temporal requirements. These requirements specify when things may or may not occur. For example, one requirement may say that when a message is received, it should be forwarded within 1 second, while other requirements imply that when a message is received, it should be processed first before it can be forwarded. And this processing takes 2 seconds. So it's obviously these two requirements cannot be satisfied at the same time because there are conflicts between them. So if there are many such requirements, the conflict can be very hard to find. That's why we do this research, and we want to help users to find these problems. So what we want to do is to partially automate the process of finding such conflicts and the process of consistency checking. And to automate this process, so obviously we need to formalize the natural language requirements into lower level logic statements. And the key problem is that such lower level logic statements, for example, on-set programming or linear temporal logic, they are always very hard to create and very hard to validate. So our solution is that we introduce an intermediate level into this process. It is another formal language that we created. To create this language, we collect a lot of temporal requirements, and we read them, and we design our language based on these requirements. And we design a formal semantic for our language, and we call it temporal action language, or TAL. Besides, we try to make sure that its syntax is easier to read and easier to validate. And by inserting this intermediate level into our process, we divide the whole process into 2 steps. First step is the front end. That is, for natural language requirement, we create the statements in our TAL language. Second step is in the back end. That is, from our TAL statement, we translate everything into lower level and process them using existing tools. The backend level, the backend steps can be fully automated because of the formal semantics, while the front end step cannot be fully automated because it starts from the natural language requirement. So in this case, every user involvement is necessary. However, we do not require users to create formal statements by themselves because it's still time-consuming. Instead, we create tools that use natural language processing techniques. These tools extract information such as the actions performed by subjects, or the property of the system, and most importantly, the temporal relationship between them. And these tools generate candidate formal statements. And all users need to do is to check these statements and correct them. And that's the main idea of my project. Thank you.
All right, thank you, Wenbin. I think I have 30 seconds. So basically, I just want to say that if you're interested in the TraceLab player, you can go to that COEST website and download it. And also that I'll be in the breakout session, as will Mark and Wenbin, if you have any interest in any of that work. And I think I have 30 seconds if there's one question.
You have 10 seconds.
I have 10 seconds.
No questions. We're going to go right to the breakout session.
Okay. Thank you very much.
Come on.